In the previous video, we looked at the basic concepts and working principles of RNN and LSTM algorithms for handling time series data. In this video, we will apply these RNN and LSTM algorithms to real data and directly implement a model that predicts cabbage prices based on past data. The coding files are available on GitHub, so you can download them and run the code yourself. The data used in this exercise are time series data on cabbage prices among agricultural products. In addition to price information, the dataset also includes weather-related factors that can influence price changes, such as daily average temperature, minimum and maximum temperatures, and rainfall. In particular, cabbage prices have a structure in which prices at previous time steps affect prices at later time steps. Therefore, randomly shuffling the data or changing their order can cause problems during model training. Because of these characteristics, this exercise uses time series models, such as RNN and LSTM. In this example, the input data consist of daily average temperature, daily rainfall, and the average price on the given day, while the output variable is the average cabbage price on the next day, that is, at time step t+1. One of the most important concepts in handling time series data is the lag effect. The lag effect refers to a phenomenon in which the impact of a cause does not appear immediately after it occurs, but instead emerges after a certain time delay. For example, even if temperature or rainfall changes suddenly, cabbage prices do not change right away in the same day. Instead, these effects are reflected in prices after several days, or even weeks. In addition, past prices have a significant influence on current price formation. Because of these characteristics, it is necessary to consider not only information at a single time point, but also temperature, rainfall, and price data over a certain past period. In mathematical terms, the current price is not simply a function of temperature and rainfall at the current time, but can be expressed as a function that incorporates information from multiple past time steps. In other words, the current price is the cumulative result of past weather conditions and price trends. A common method for feeding time series data into a model is the sliding window approach. A sliding window refers to a technique in which training samples are created by extracting fixed-length, consecutive sequences from time series data. Using this method, the model learns patterns over a certain period in the past and predicts the value at the next future time step. In actual code implementations, the length of this sliding window is usually called the sequence length. The code shown here is an example of how a sliding window is implemented. As the loop index I increases, the window moves forward along the time axis one step at a time, and each data segment corresponds to sequence length. The sequence length is an important hyperparameter that determines how much past information the model can remember. It can be set based on domain knowledge or selected experimentally using methods such as grid search. If the sequence length is too short, long-term patterns or cumulative effects may not be sufficiently captured, leading to higher variability in the predictions. On the other hand, if the sequence length is too long, unnecessary historical information may be included, increasing computational cost and raising the risk of overfitting. This slide visually illustrates how time series data in an Excel file are structured as inputs for RNN and LSTM models. First, the input data consist of three variables: daily average temperature, rainfall, and the average price on the given day, while the output variable is a single value, the average price on the following day. Therefore, the input dimension is 3 and the output dimension is 1. In this example, the sequence length is set to 30, meaning that the model takes 30 consecutive days of past data as one input sequence. In the first window, data from day 1 to day 30 are fed into the model. And based on this information, the model predicts the average price on day 31. In the next step, the window moves forward by one time step, using data from day 2 to day 31 as input to predict the average price on day 32. In this way, the sliding window moves one step at a time, generating a series of overlapping training samples. Through this process, the model learns not just information from a single point in time, but the patterns of temperature, rainfall, and price changes over the past 30 days. By effectively capturing this temporal dependency, the model can predict future cabbage prices more accurately. This slide shows the typical structure of RNN and LSTM models, in which the hidden state at each time step is passed sequentially to the next time step. In this example, the sliding window is set to 30, so a single training sample consists of 30 consecutive input time steps. The input at the first time step is denoted as x1, the input at the second time step as x2, and in the same manner, the input at the 30th time step is sequentially fed into the model as x30. At each time step, the RNN or LSTM computes a new hidden state using both the current input and the hidden state from the previous time step. This hidden state is then passed on to the next time step. As a result, information from x1 to x30 is accumulated and reflected through the hidden states, and the model is trained to predict the price on the next time step, that is, day 31. Now, let's implement this step-by-step in code. First, we import libraries for data processing and visualization, such as Pandas, NumPy, and Matplotlib. We also import the min-max scaler and TensorFlow Keras modules, which will be used later for data normalization and for building the RNN and LSTM models. Next, we load the Cabbage price dataset and store it in the variable df. This dataset contains daily records of cabbage prices along with weather information. Since the temporal order of the data is crucial in time series analysis, we sort the data in ascending order by date using the sort_values command. In this step, we split the data into training and test sets, while taking the characteristics of time series data into account. Unlike typical independent and identically distributed data, the flow of time itself carries important information in time series data. If the data were randomly shuffled, it would no longer be possible to predict the future based on the past. Therefore, in this example, the data are not shuffled. Instead, the first 80% of the data set, taken in chronological order from the top, are used as the training set, and the remaining 20% at the end are used as the test set. In this way, the model is trained on past data and then evaluated on a future period that it has not seen before. After splitting the data, the input variables x consist of daily average temperature, rainfall, and the average price on the given day, while the output variable y consists of a single value, the average price to be predicted. Finally, data normalization is performed, and the printed output allows us to verify that the total number of samples and the sizes of the training and test sets have been split correctly. In this step, we perform pre-processing to prepare the test data as input for the model. Since the test data come after the training data in time, using the test set alone would result in insufficient past information, making it impossible to generate the first prediction. To address this issue, the last 30 days of the training data are concatenated in front of the test data, forming one continuous time series. This ensures that, at the beginning of the test period, the model still has access to a full 30-day history and can perform predictions properly. After this, the test data are normalized using the scaler that was already fitted on the training data. This is an important step to prevent information from the test set from leaking into the training process, thereby avoiding data leakage. In this code, the data are structured using a sliding window approach for time series prediction. The build underscore dataset function groups 30 consecutive days of data into a single input sample, data X, and uses the cabbage price on the following day, day 31, as the output value, data Y. The sequence length is set to 30. In the first RNN or LSTM layer of the model, the value 64 represents the dimensionality of the hidden state. When return underscore sequences equals true, the model outputs all 30 hidden states computed at each time, step from day 1 to day 30, and passes them to the next RNN or LSTM layer, forming a many-to-many architecture. In the input dimension, the value 3 refers to the number of input variables, which are daily average temperature, rainfall, and average price. Finally, the output dimension of 1 in the dense layer indicates that the model is designed to predict the average cabbage price for the next day as a single scalar value. In this step, we train an LSTM model and a basic RNN model separately and compare their prediction performance. Both models are trained on the same dataset under identical training conditions, 30 epochs and a batch size of 16. After training is completed, predictions are generated on the test data. The predicted values and the true values are then converted back to the original price scale using inverse underscore transform, allowing the results to be interpreted in terms of actual cabbage prices rather than normalized values. Through this process, we can compare and analyze how RNN and LSTM differ in their performance on cabbage price time series prediction. In addition, during model training, we can observe that the loss value gradually decreases as the number of epochs increases, indicating that the models are learning effectively. In this step, we visualize the model predictions and quantitatively compare them with the actual prices. The first plot shows the entire cabbage price time series, including both the training and test periods, allowing us to observe the overall trend and variability of the data. The second plot focuses on the 20% test period that was not used for training and compares the actual cabbage prices with the predictions from the LSTM and RNN models. Each predicted value is generated sequentially on a daily basis, using the previous 30 days of information as input. In other words, for each date in the test period, the model predicts the next day's price based on the temperature, rainfall, and price data from the preceding 30 days. Finally, the RMSE is calculated to numerically compare the prediction errors of the two models. In this experiment, The LSTM model shows a lower RMSE than the RNN model, indicating more stable and accurate prediction performance.